This is a notch filter for 116 MHz with 3 crystals. The notch is about 48 decibels deep and the attenuation 10 kHz away from the notch is 5 decibels, and 20 kHz away it's 4 decibels. And this is intended to be used to measure noise from an oscillator on 116 MHz. Here is the response spanning over 1 MHz instead, and you can see there are many false resonances, spurious resonances on the high frequency side. This is typical. I'm looking at the oscillator of an Anglian 3 converter, extracting the signal from this point. IC5 is removed. Looks like this. The signal goes into a directional coupler here and a 6 dB attenuator on the far side, because I want the impedance to be reasonably close to 50 ohms when I connect the crystal filter there. And at this time I have 60 decibels of attenuation instead of the crystal filter, followed by a low noise amplifier, and then into the spectrum analyzer. The signal level right now is minus 30 dBm. I have this signal generator now 20 kHz below the crystal oscillator in the Anglian transverter. I switch it on and set the level to be 50 decibels below the crystal oscillator. You see, minus 30, and I move the marker and read minus 80 here. So I know this calibration signal is 50 decibels below the signal I'm going to investigate. And I switch it off and set the bandwidth, video bandwidth, narrower, let's say 30 Hertz. And now I want to check the performance of the spectrum analyzer in terms of what is the limit, where is the sideband noise or maybe amplifier noise. And at this frequency, 20 kHz below, I can read minus 105 dBm. I will make a table for the different frequency separations. This is what I find. The noise is down to minus 109 dBc per hertz, and at 10 kHz it's minus 97.9. So it is safe to use this amplifier, this one with the PSA 4 5043, because the amplitude modulation it produces is much below 110 dBc per hertz. I will replace the attenuator by the crystal filter. Here is the crystal notch filter replacing the 60 dB attenuation. And it goes into this amplifier as before, and this is what I see on the spectrum analyzer. The signal generator, this one, is now at minus 21 dBm, and if I switch it off, I can see that the crystal oscillator is at minus 21.2. So the attenuation through the filter is 51 dB, a little bit better than I could see on the network analyzer, probably because of the phase noise in the network analyzer. I will measure the level of the test signal that I know is 50 dB below the crystal oscillator, and I will do that every 10 kHz below the crystal oscillator. I can now switch off the signal that is 50 dB below the crystal oscillator and look at the noise floor of the crystal oscillator. And it looks like this. It has irregularities on the low frequency side. I don't know what that might be caused by. But it seems to be a property of the oscillator. I will look what the levels are. When looking at the wider frequency range and with 1 kHz video resolution, I can see on the noise floor that it jumps up and down by nearly 10 dB. I don't know the reason for this, but before trying to eliminate it, I will see what the average level is by going back to the narrow range and slow video. Here in this part is the noise from the crystal oscillator when run through the 60 dB attenuator. On the carrier the level was minus 30 dBm, and then at different frequency separations, like you can see in the column. This is dBm, and here is dBc per hertz. The numbers happen to be the same because the bandwidth is 1 kHz and the level was minus 30 dBm for the carrier. The next is when I ran the signal generator through the notch filter. At the crystal oscillator frequency, the level was minus 70. And then 10 kHz, minus 23, minus 21, and so forth. Then I switched off the signal generator and switched on the crystal oscillator and look for the noise level at different frequency separations. Now, of course, at frequency separation 0, that's not noise, it's the carrier that goes through the filter. The level is minus 21.3. And then here are the observed noise levels. And they are very uncertain because of the variations of the noise floor. From that I compute the dB below the carrier that is present to the spectrum analyzer. It means this carrier. And here I get dBc per hertz. At 10 kHz, 97.7, it happens to be very close to the value I have from the spectrum analyzer itself. So this means that the contribution from the noise from the local oscillator in the Anglian must be well below these 97.7. But this is on very close to the carrier that leaks through the filter, and this means that it is not only noise, it's also part of the carrier. So I cannot really draw any conclusions. I can say it is probably below 100 or something. At 20 kHz I see minus 101.7, well, minus 102. So this is probably minus 100, but I disregard this. This minus 102 is well below minus 106, and it's far away enough so I know it's noise only. These values compared to these values give a difference like here. It means that the contribution from the sideband noise that I'm interested in has to be not quite 3 decibels below this value, means equal to the values observed here. So a little bit higher, because this is a little bit more than 3 dB. At this point, the noise I see here is 50% from the spectrum analyzer and 50% from the crystal oscillator, so means minus 108 or minus 108.5 perhaps. Anyway, I correct for these numbers to come to this conclusion. Then there is one more thing. This is a spectrum analyzer with a logarithmic detector. The noise values have to be corrected by 2.51 dB. The logarithmic detector shows a value that is 2.51 decibels too low when the signal is noise compared to a true RMS detector. So I add 2.5 dB to this column and get these results. And then I compare these ones with the level of the generator at the same frequency. This is to compensate for the characteristics of the filter. The filter has some loss and it varies a little bit with frequency. So this table, this column minus that column, gives me this final result for the sideband noise of the LO itself without the buffer amplifier. Now this is while it is still disturbed by this instability on the noise, so the real performance is a little bit better than this. I have to add 80 dB to the direct difference between this column and that column, and that is because the carrier of the signal generator, this one, is 50 decibels below the crystal oscillator of the Anglian, and 30 dB because the bandwidth is 1 kilohertz. And this is the results in dBc per hertz. Well, look at the spectrum analyzer and the instability of the noise floor here. It can vary. If I turn the marker, you can see down to 98 and up to 94. And I'm looking for the lowest values at some, let's say, 20 kilohertz. To wait a little while. Well, yes, here, minus 97 at 24 kilohertz. Here we had minus 98. Here, minus, well, 97. So this is some instability. I have seen this phenomenon before, and I have written about it on my homepage many years ago. You can find it on this URL. It's on the WSE converters I made about 15 years ago, checking wide range reciprocal mixing and noise modulation. You can go there and read the text. The important thing is here. Here is a poor soldering. And that results in noise modulation, amplitude modulation sidebands. And at levels close to the level we see here, maybe not quite as strong, but anyway strong enough to be a problem for this receiver. And if you look at this, here we get focus. Well, the light is not favorable, but maybe you can see that this PCB is pretty ugly by now. I've been soldering and desoldering and soldering back again, and very probably there are some, well, there is one at least poor soldering somewhere, and I don't have the tools to work properly with surface mount, so I don't think I will find it. I will try to reheat some soldering joints, but I don't have much hope that it will help. Anyway, the local oscillator is good enough, even with this extra noise added to it. I think I found the problem. Look here. That's when I move this trimmer capacitor. This one. It's a ceramic, very small capacitor. It seems to have an unreliable connection between the movable part and the rest, the ground. So I replaced that ceramic trimmer with a plastic trimmer that I hope is more stable. And indeed, looking at the spectrum analyzer, the problem has disappeared. The noise floor is stable now. It has a little hump somewhere here occasionally. Well, maybe not. And the value I can see, if I read the marker, minus 97 dB at 25 kilohertz, and at 50 kilohertz minus 99. So I think the oscillator is fine in this box now, with the modifications I have done to it. I have added the buffer amplifier, this one, PSA4 5043, with a big capacitor on the input. And that is required then to have these very big capacitors to decouple the 5-volt line, because that has to be quiet for low frequencies when decoupling low frequencies to the 5-volt line like this. By the way, this is no longer a 100 ohm resistor. I put an inductor there. And the output, I have connected the output to my test system and disconnected what was before sitting on the output here, 1 nanofarad into a filter. I removed the filter and put the 60 dB of attenuation back, and look at the screen. And it turns out the gain of this amplifier is very low. It is heavily saturated, and the level is now minus 27 dBm. So it's only 3 dB more than before. I want to keep the signal generator, the test generator, 50 dB below the main signal. So I want this to be what would it be? Minus 27, that means minus 77. So I go up a little bit. Minus 77 dBm. The signal generator now reads minus 19 dBm. And I know the level is 50 dB below the level of the crystal oscillator. This means that I should compare the noise floor to a level of plus 31 dBm. It doesn't mean I have plus 31 dBm because the notch filter stops the carrier and then I have this amplifier afterwards. But the noise reading I get here, that is minus 87, should be compared to plus 31. This sums up to minus 148 dBc per hertz. And it's clear the noise floor is now much higher than it was before, if you compare to the carrier that goes through the filter. And minus 148, that's very similar to what I saw on the entire transverter in a previous video. Now I shouldn't forget this, so rather than minus 148, it is minus 145.5 or minus 146 something. Minus 145 perhaps. The bad thing about the noise added by the buffer amplifier, the PSA4 5043, is that the noise is wideband. It is not much closer near the carrier than 1 MHz away. This is span plus minus 2 MHz. You can see the spurious resonances of the notch filter removing some noise on the upper side of the signal. This is the schematic diagram of the oscillator as it looks now in my modified unit. What you see here is results I obtained previously when measuring the receiver side without the input amplifier. And it looks very similar to what I found today. Minus 148, and this was minus 150 at 50 kilohertz. And I think actually I didn't evaluate it, but it went down probably to this value. And I couldn't measure as close as 10 kilohertz with a spectrum analyzer. Now, whether it is reasonable to do these modifications on the oscillator that I have done, to bring the noise at this point down to, was it minus 156 or something, it doesn't do probably much good, because the noise from the IC5 here is dominating on the LO side. The big change on this unit is just to replace the SPF4 5043 by PSA4 5043. This gives a significant advantage. And it could also be good to decouple the input pin for low frequencies, but I'm not really sure it is going to be worth it. And you can do that on this LO chain and on the transmit side. On the receiver side, the IC will oscillate on low frequencies. One has to add some more components there to attenuate oscillations at low frequencies.